I'm gonna give a broad overview of data visualization beyond the basics. My name is Fernando Becerra, and I'm gonna talk a little bit about me. So I got a PhD in astronomy and astrophysics in 2018. After that, I decided to leave astronomy and started working on information design. I spent a year at Fathom Information Design at Boston, working creative, interactive applications, data visualization. This is one example of the things that I did in my free time. They also allowed me to create my own personal projects. So this one is an exploration of Bob Ross paintings. So what I did was basically get all the transcripts from the episodes of The Joy of Painting and analyze them. And based on that, I also made an introduction to explore all the paintings that Bob Ross did during that show. Well, this is kind of like the fun project. Of course, I did more useful stuff for clients. But this is one of the reasons why I started doing data visualization, because I really like this kind of like playful, interactive thing that allows people to learn and understand things. I also took some time off after that. I started traveling. Maybe that's one of the stories that people might be interested in. But now I'm working as a data science and data visualization freelancer. So I'm working from home. I'm in Chile right now, and I'm going to talk about data visualization. So let's start from the basics. So what is data visualization? I'm going to give a broad overview of what it is and what resources do we have to improve a data visualization, to make it better, etc. So let's start from the very beginning. This is the definition. So what is visualization? Visualization is the formation of mental visual images. The one that we use more often is the second one. It is the act or process of interpreting in visual terms. Oh, sorry. The act of process of interpreting in visual terms, or of putting into visible form what data usually. The whole point of data visualization is to convey information through graphical representations of data. And the kinds of data visualization that we commonly use are stuff like this. These are plots that I did for one of my papers in 2015. This is visualizations of the simulations that I was running back in the days, and these are plots of accretion rates, and these are very common in astronomy papers. As a grad student, I studied the formation of the first black holes in the universe. So what you're seeing here is the formation of one of those supermassive stars that eventually will lead to the formation of the first black holes. And when I talk about data visualization, I'm not only referring to static visualization like this one, but also to movies. And movies are very useful in, for example, presentations. They allow you to communicate way more things than what you will do by presenting a static image. So what's the goal of a visualization? Well, broadly speaking, there can be three goals: to record information, to analyze data, or to communicate information to others. So one example of recording information is the visualization that Galileo Galilei did of the phases of the moon. Basically, he was drawing whatever he saw with his eyes. So this is just the pure motivation of this is to record what he was seeing. One example to analyze information is this map. This was done by Jon Snows in 1854. In London, there was a cholera outbreak in 1854, and people didn't really know what was going on. So his idea was to plot every case in its current location in the city of London. And what caught his attention was this huge amount of cases in one place. And he also noticed that there was a pump around it, like very close to it. There are more pumps, but it was this one particularly that was provoking this increase in the cases around this corner. So he made the connection that it might be something in the water that might be causing this disease. And yes, that's how they figured out that it was water, contaminated water, what was causing the cholera outbreak. So that led people to actually realize what was going on and fix it. Thanks to that, they saved lives. This is an example of trying to communicate information. So this plot was done by Florence Nightingale in 1856. So what she's plotting here is the causes of deaths in the Crimean War. So pink is people dying from wounds in the battle, people dying from other causes, and the bluish is people dying from diseases. And as you can see from this plot, is that most people are dying from disease. This means that they are not dying from injuries from the war, they are doing because of the poor hygiene conditions in the hospitals. That also led to a change in policy, which improved the quality of the hospitals, and they saved lives by adopting those measures. A final example is this map by Joseph Minard in 1861. This is a map, but at the same time, he's plotting the size of the armies. So this is a plot of the Napoleon army in its campaign to Moscow. So they started here, the width of this line is the number of people in the army. So they started with more than 400,000 soldiers. And as they started getting close to Moscow, they were losing more and more people. Finally, they reached Moscow with just 1,100 soldiers, and they start going back to France. And as they go back, the winter hits, you can see the temperature here. So temperature starts decreasing, it's getting colder and colder, more people are dying, and finally they arrive with only 10,000 people back to France. It's also interesting to see that as they go back, here, some people, well, it was pretty cold back then, so some people decided to cross the river. Some people decided not to cross the river, go back and take an alternative route, and you see that 6,000 of those people joined the original army back in France. So this is a lot of information. It's telling us a story about the army, what happened, how many people died, how cold it was. So this is a very, very nice blend of many information, of a lot of information in just one single plot. So why is data visualization so important? Well, for that, I'm going to use this example that's called the Anscombe quartet. So these are 4 data sets, set A, B, C, and D. Different data, but if you see here, they have the same statistics. They have the same mean, the same standard deviation, the same correlation, and the same linear regression. So the point here is that if we focus on just these values, then we don't see any difference between these sets. But once you plot them, you clearly see that they are not the same and that there are differences. So sometimes just numbers, just statistics is not enough. So in this case, plotting these data sets reveals something more. It reveals something that is hiding in the data and that we can only see once we start playing with visualizations. So that's why it's really important to make data visualization, because it allows you to discover new things in data sets. So now moving into more like advices to improve your design, we're gonna make a test. So this is an activity, and I want you to try to think about 3 kinds of visualizations that you will do for these 2 quantities. If I tell you 42 and 23, how would you plot that in any way that you can come up with? If you think about it, how can you represent these 2 numbers? Take some time. I'm gonna give like a minute for you to think about it. If you have pen and paper around you, you can draw some sketches and just like let your imagination come up and start thinking about how to visualize these 2 quantities. So the idea behind this is more or less to see what kind of plots you already know, right? So this is gonna be a guess, but I guess that most people would think in terms of pie charts, bar plots, scatter plots, or just an Arabic representation of the numbers. If you did think about these kind of plots, then probably this is an example of design fixation. which is like the preconceived ideas that we already have. And this kind of plots, scatter plots, line plots, are very common in papers, especially in the astronomy field. So we tend to think of those plots as the most common ones. But the truth is that there is more ways of representing the same number. So this is a webpage called 45 Ways of Representing Two Numbers. They are using 75 and 37 here, and they explore different ways of representing it. So by using icons, by using people icons, by using big squares and small squares for tens and units, bar charts. But at some point we start getting more creative. So we start using gray tones, colors. We can envision those two numbers as a pair of coordinates in the Cartesian grid or polar. Or we can also see these two numbers as geographic coordinates. So the numbers are just numbers, but they can represent data. In this case, for example, they can be associated with countries, some values, quantities, statistics, whatever. But the whole point of this is just to think a little bit more about what numbers represent and what's our intention on representing those numbers. So what are the best techniques to do data visualization? So Jacques Bertin already defined some visual variables, and I want to make clear that we are already aware of these things, but there's a lot of theory behind what we do every day when we're making a plot. So Jacques Bertin defines three basic units that he calls marks. There are points, lines, and areas. And there are ways of modifying those three basic units that are called channels: position, size, gray value, texture, color, orientation, and shape. And we already use variations of these combinations. So for points, for example, when we create scatter plots, we use different shapes, we use dots, triangles, squares, etc. We use different colors for different groups. We use crosses, etc. For lines, we use thin and thick line. We do dash, dot, dotted lines, solid lines, dash dots, and a whole combination of them. For zones or areas, we use shaded, we use different colors, etc. So everything that we use so far has a theory behind it. And some of them are less efficient, less effective in communicating things, and some of them are more efficient. So for example, for quantitative data, position is way more efficient. That's why we like scatter plots. It's easy to find a value, and we do it without any problem. Length is also another one that is really easy to differentiate. That's why we also like bar charts. Once we start getting to the angle or the slope, it gets way more complicated. Same thing with area and intensity, and color and shape. But color and shape can be very useful for other kind of data when there are like different groups of data, for example. By the way, because angle is not so easy to distinguish, is one of the reasons why pie charts are so bad for this. We will prefer bar charts, and we're gonna see some examples of that later. So there are some design principles defined by Edward Tufte that are really, really useful once you start thinking about how to present information. Those are: first, graphical integrity; two, the light factor; three, maximize data to ink ratio; and four, avoid chart junk. So let's see some examples of each one. Well, not surprisingly, you can see examples of graphical integrity on Fox News. The problem with this chart is that the baseline is not at 0. So remember that I told you that one of the more efficient ways of representing data is the length. Here, bar charts depend on the length. And if you cut the baseline, then the length is different. So we see this as a huge increase, but 1 million out of 6 million is not that much. So if we do the baseline in 0, this plot will look totally different. And there's another component of graphical integrity that is the intention. Do people intend to do this? Do they do it on purpose? And it might be sometimes that it's a one-time mistake, but if you keep watching Fox News, I hope you don't, but if you keep watching Fox News, then you're gonna find this kind of mistakes all the time. this line is not straight. The, the, the difference in periods between the dates and the numbers just doesn't fit. This is like a really bad graphic. And again, another example from Fox News. So data visualization, the way they communicate data is so powerful that it can also be used to lie about charts. And there's a whole book written about this. It's called How Charts Lie from Alberto Cairo, in case you want to read it. The second point was the lie factor. And this example is from Steve Jobs. So he's presenting this 3D pie chart. The green one here represents the share of the market of Apple. The purple one is the share of the market from others. And if you compare them just from this image, the green one looks bigger, right? This is the 3D version, this is the 2D version. In the 3D version, the problem here is that we're adding this series of pixels, green pixels at the bottom, that they don't add any information to the plot. So these are not for information purposes. This is just like aesthetic purpose to make it look 3D. And because of that, this green slice looks bigger than the purple one. Although the numbers are the opposite. The purple one should be bigger. You can also improve this plot by just doing a bar chart. This is much better and it's easier to compare different bars. The third point is the data ink ratio, which is defined by the ink that you use to represent data divided by the total ink you use in a graphic. And another example of this case is a 3D plot. We want to maximize that ratio, meaning that we want to use more ink to represent data. But again, in the 3D, all of these pixels on the top of the bars are on the side of the bars, they are not adding any data to the plot. So we can easily get rid of them, do a 2D plot, and it's way more efficient in terms of the data ink to ratio. As you can see now, there's a trend, just avoid 3D graphics. They are like bad and they are not communicating effectively as the 2D versions are. And the last principle is avoid chart junk. We really like adding stuff to our plots, when in reality, sometimes it's just not needed. The simpler, the better. So this is one example that we can start like taking some elements of the plot to make it look clear. So for example, we can get rid of the grid, we can get rid of the background. And this one is a very classic plot done by the default matplotlib in Python. Every time we make a matplotlib plot, it comes with this border, an x-axis, a y-axis, and whatever data we're plotting. But we can go further and keep removing more things. So for example, the border is not needed. If we push a little bit further, the y-axis is not needed, because now we can clearly identify this as 15%, 10%, and 5%, and it's actually very nice to see. And a little bit more, we can get rid of the sticks and the baseline. So this is the same plot, it's way cleaner, it's simpler, and it communicates more efficient. So in summary, we have Edward Tufte's design principles: 1, graphical integrity; 2, the lie factor. This one, don't be like Fox News. The second one is don't be like Steve Jobs. 3, maximize data ink ratio. And 4, avoid chart junk. Another interesting thing that is very useful for data visualization is perception, is how we humans process information, how our eyes react to information. So Colin Ware, in his book, Visual Thinking for Design, defined 3 visual channels: contrast, motion, and color. So this comes from back in the days when we were like living in caves and stuff, and we had to be aware of our surroundings for any danger, like a predator or like whatever. We had to be aware of contrast, like something hiding in bushes, or motion, something moving, just like a survival instinct. And all of these things can be used for data visualization to improve our ability to recognize patterns and to draw your attention. As a side note, that also can be used by the advertisement industry to call your attention and like make you buy stuff. So let's go into the details. Contrast. Contrast can be achieved in many different ways. We see 16 examples here, like gray value, elongation, shapes, curvature, adding a surrounding box, etc. Sharpness, blur, this is using photography, etc. So there are like many ways of creating contrast in the data set. If you want to draw the attention of the user to one single dot, sorry, you can do it in many different ways. Motion is another thing that calls our attention, especially when someone has the laptop open in a conference talk or like in the middle of the class and something moves on the screen and you tend to move your head and like pay attention to what's going on there. It's like very easy to get distracted by motion. And people use this to hold your attention too. And finally, color. Color is very important because of it adds information to the plot, but it also adds beauty depending on the color scale that you choose. And I decided to recommend this tool, Color Viewer, that has a very nice palette of colors. Most of them are already integrated in Matplotlib and in other visualization libraries, but this is really nice. And it's very powerful how you can express information and emotions through colors. In terms of color maps, the ones I would recommend are these 5, Viridis, Plasma, Inferno, Magma, and Civilis. This is less common, but it's also pretty good. They have many advantages with respect to the other ones that we were used to. So they do well when they transform into grayscale. I graduated in 2018 and people were still printing papers in black and white. So it's useful to have a color map that translates well into a black and white printer. Same thing for color blindness. We usually are like not aware that colorblind people might be seeing our papers and like reading our information. So these are very friendly to colorblind people. And also, I cannot emphasize more that you should not be using the rainbow color map. This is really bad. It is bad because it translates really badly into grayscale. The blue and the red looks kind of the same, so it's hard to differentiate a sequence. But also because it creates these sudden drops in information which are not like that in the actual information. So because of the color we choose, we emphasize these differences, but in reality, the data is not that different. This happens in transitions between blue and green and between green and red. So it's a really bad color map, and I'm glad that it's not the default color map in Matplotlib anymore. So as a summary, we have 3 visual channels that we can use to draw the user's attention to a particular point in our plots: contrast, motion, and color. Now,
Fernando, sorry to interrupt. We have a question from Miles Cranmer about what do you think of Turbo, the new rainbow color scheme in Matplotlib?
Oh, I'm not aware of that one. That's a good question. I think I might get back to you later after the talk. Yeah, because I'm not aware of that one.
I think they recently introduced it to try to eliminate the issue when you convert it to grayscale, but I have no idea if it solves the other issues. I was just wondering if you heard of it.
The rainbow color map is really bad, but there are other alternatives that are nicer to the eyes and they translate better in grayscale. But I'm not aware of the turbo color map, so thank you for mentioning that. But I might do some research and get back to you later. Are there any other questions? No? Okay. So another important point here is how we interpret plots. And Gestalt principles try to explain how we group dots in our minds. And for that, they explain 4 principles: proximity, similarity, connection, and enclosure. And after the example, it's gonna be clear to you. So here, for example, proximity. We have that there is a group here on the top left. On the top right, we see two groups just purely based on proximity of these dots. Even though they might have different colors, as you see at the bottom, we still interpret those dots as two different groups. So proximity can be used to let the user know that we are talking about two different data sets, or two different groups, or two different subsets, etc. Similarity can be used in a similar way. In this case, we're using colors to emphasize that squares of the same colors might belong to the same group, and regardless of their orientation. So on the left, we see vertical. On the top right, we see horizontal. It doesn't really matter. We just focus on the colors. And that color is telling us that they have a shared property. They share something. Connection is another way of making relationships between two different points. And we can see the contrast between connection and proximity in A, connection and color in B, connection and size in C, and connection and shape in D. So independent on the color, proximity, size, or shape of the dots, if we just like draw a line between two dots, we interpret that as a connection between both of them, as a relationship between both of them. And finally, there is enclosure. So if we start from similarity, we have circles and squares. Then we have connection, we add lines. Now squares and circles are related somehow. We can add another layer with enclosure and say, okay, there's also a relation between these two, right? So these are just 4 different ways of telling the user these dots are connected, or these dots belong to the same group. So all of these are techniques that we can start adding to our visualizations to draw the attention of the user. Another important point is the message that you want to communicate with your data visualization. And in particular, the place that you can use to communicate your results is the title. I think in general, we tend to neglect the title and just like put a very descriptive title, like number of stars as a function of time, instead of telling the results through the title. Something like the number of stars decreases as a function of time will be way more useful to whoever is reading that plot. In the same way, we can use saturation to draw the attention to the main point in the plot. For example, in the case of the chocolate here, we see the bar has a different saturation of blue, and our eyes just go straight to chocolate. And then we read the title and we know that chocolate is the most popular flavor. So with that being said, yep.
Quick question, Fernando. So a lot of the recommendations that, well, surely our perception of visualization is relative because all of our brains work differently. So surely different principles will work more effectively on different people, such as, you know, color or shapes. So, and that's I suppose that's hard to, like, you can't predict that in advance unless you know, like your specific audience might be very, you know, into numbers or shapes, and maybe you can adapt that. But yeah, I don't know if you can say a few words on that.
So yeah, so there are some general tendencies that people share, like, for example, I was talking about contrast or motion. So that happens at a subconscious level. You don't even realize when you're paying attention to something moving. You just do. But you're right, and that's a very important point of visualization to know your audience. Like papers, for example, are mostly written for other scientists. So we share a common language, so we know how to read a scatter plot, a line plot. So we know more or less what will work with that audience. But once we do outreach, for example, the audience is different. So we need to use different cues, different kind of representation. So you're right, like it's a very important point to know your audience and how they might react to your visualization. And so moving to types of charts that we have, these are very common charts. Most of them can be found in papers, depending on what's the purpose of your visualization. And that's another point that I want to emphasize, the purpose of your visualization. What do you want to communicate? What's the main point of your visualization? Depending on that, depending on whether you want to show a relationship between two variables or comparison or distribution of composition, depending on that intention is the kind of chart that you're gonna use for your data. And there are many. These are just the basic ones, the ones that we are used to, the ones that are most common in astronomy. But there's also like different kind of representations for trees and networks. There are representations for maps. These ones are gonna be super popular during election time because maps like the color plate is used to represent votes per county or per state. The ones on the right, the symbol map was very popular during the COVID-19, showing number of cases, etc. There's also ways of representing text, word tree, document burst, stream graph. The stream graph is very useful to visualize how a word is used as a function of time. There are also ways of representing high-dimensional data. We have scatter plot matrices, polar plot, and parallel coordinates. I really like parallel coordinates in particular. They can reveal a lot of things that you don't usually see. And my last point, and it's also a very important one, is storytelling. It's the story that you want to communicate with your data. Behind any visualization, there's a story behind it. There's a story of how you gather the data, how you explore the data, how you interpreted the data, how you found your results in the data, and that's the story that you have to tell to whoever is reading or seeing your results. And I'm gonna go through a set of examples here that are really good at storytelling. Most of these plots are interactive, which is another level that you can add to a visualization. So you can let the user explore the data by themselves. This case is a plot of exoplanets. The y-axis is the mass of the exoplanet, and the x-axis is the distance to the star. And they call this Goldilocks because this zone is just right. Closer is too hot, farther away is too cold, so this is just right. And through text and interaction, they tell you a story of how hard it is to find exoplanets in this box, and this box is the habitable zone. So it's a really nice way of learning about this, and once you learn about the habitable zone, you have the freedom to go and explore the rest of the dots. Another example is the satellites orbiting the Earth. So this visualization is also interactive. You can see the information in each one of these dots. The size of the circle represents the weight of the satellite. The color is the country, and as you might guess, the blue is the US. It's really nice also because if you scroll down, you start to see the satellites that are closer to the Earth. And also they use text to tell you the story of this, how we ended up with like thousands of satellites around the Earth, and like at what year we reached a spike and like started like sending satellites. It's really nice. Another visualization that is not that interactive, but is very revealing, is how effective vaccines are. So here we are plotting the number of cases of polio per 100,000 people by state for each year. And we start to see that this like more than 100 cases per 100,000 people in some of the states. And they mark in 1955 when the vaccine was introduced. And we immediately see a huge drop in the number of cases. Nowadays, we don't even have that many. So this is very revealing to say how effective vaccines are, that the introduction of the vaccine, like not completely, but almost eradicated the polio from the US. And this story is just there, like doesn't need too much text, it's just like showing the numbers in a way that is so easy to process that you immediately realize the importance of vaccines. This example is just to show you that that data visualization can be beautiful too. So this is a 3D model of the Earth. The green particles represent the wind speed at the Earth's surface. And you can go to this website. It's really cool to see how everything moves. It's just very beautiful. They've done artwork from it. They sell it also. But the point here is that visualization, it's about information, but it's also about beauty and wonder and like appreciating how information can be beautiful too. I have a clip here. I'm not sure if I'm sharing audio from the from my
you
laptop.
can share your audio in principle, I think, but
yes, I think I didn't choose it. Yeah, I didn't choose it. Okay.
I think it's on it's on the top somewhere.
It's on the lower left corner. So let me know if you don't hear the sound. But this is a clip of hands rolling. This is a masterpiece of storytelling with data. So I'm not gonna even comment on this. I'm just gonna let you watch it and I'll be done.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health, life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400,000, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you have seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
Pretty neat. Yeah. Okay, so as a summary, remember visualization goals to record, to analyze, and to communicate data, information. Jacques Bertin's visual variables, marks and channels, Edward Tufte's design principles, graphical integrity, don't be like Fox News, the life factor, don't be like Steve Jobs, maximize data ink ratio, no 3D, avoid chart junk. Visual channels, contrast, motion, and color, Gestalt principles, proximity, similarity, connection, and closure. Remember to tell your message and remember to tell your story. Thank you.
Thank you, Fernando. I actually have a question I meant to ask earlier. So
Sure.
obviously video is great to visualize stuff, and some of us, like some fields of astronomy and astrophysics, don't necessarily need much of video, but like what you showed earlier, like, simulations and everything that's 3D or higher dimensions, you definitely would like to show video. And of course you can't do that in paper. So what's your experience? And perhaps other people in the crowd can comment on the experience of trying to publish videos with papers or in papers or as attachments and that sort of stuff.
Yeah, so I haven't done it myself in papers, but my recommendation would be to just include a link on the paper, a footnote or something, because people actually go and click on those links and they watch the videos. I made one, it's on my Vimeo channel. I made one because a French magazine was interested in publishing my simulations, and they published in the printed version the images, but they added a QR code with the link to the video, and a few hundred people went and see it. So it's always nice to add videos, and also for presentations. Like in presentation, you have the advantage of being able to play videos, so just use that to your advantage and to communicate the visualization. But also, like in the last example, the Hans Röhling example, that was supposed to be a scatter plot, but since he saw that evolution in time, he made it into a video. So eventually there are other ways of seeing data, to thinking about data that can be expressed as a video instead of just a static chart.
And if I can just jump in here.
Sure.
So I'm affiliated with AAS Publishing, so I know a little bit about this. And so actually we publish a lot from people in the solar community, and they use a lot of videos. Like you see tons of, flares erupting, and that stuff is actually pretty prevalent. And obviously you can't put a video in a PDF, but at least the AAS journals do. Videos are first-class content items, and actually are, most of us look at PDFs, but technically the version of record of the articles is the HTML form, where you can embed these things. Although I think one of the big challenges that we have is getting it to a point where people actually want to look at the HTML instead of the PDF, which is going to take a lot of work. But if you want to see how people handle it right now, go check out the solar literature, because there's a ton of this stuff.
But that's an interesting point, actually, because moving the PDF to a HTML doesn't add anything, right? So the medium is also like, depending on the purpose of sharing the video, maybe the best idea would be to modify the paper in such a way that it becomes something that can be used on HTML, right?
Yeah, I mean, the HTML is a native form, and it does have things like videos and interactive figures that can't be expressed in PDF. So, you know, you can think of it as like our fundamental model for what you can put in a paper is more flexible than what can be expressed in PDF. But just empirically, in practice, people like being able to download a single file and print it out. So, so yeah, people will look at the PDFs, but actually what we support is broader than what you can do in a dead tree format.
Thanks. Are there any other questions? I have some tutorials that I don't have much time, but I'm gonna go through them to explain what they are and how you can access them. They are gonna be available on the GitHub repo Astro Hack Week.
Yeah, so if you haven't done so, please, everyone, try to access the tutorials and see if you can play with the Jupyter Hub, because it's a really nice resource that we have for all of you, so that you don't have to run code on your own machine. It's all done remotely.
Yeah, speaking of that, I already added them to the Jupyter Hub. So if you want to access them, so once you log into the Jupyter Hub, it's gonna take you to this address, your username, and then 3. You can change that to lab, and it's gonna show you this. And there you're gonna have a console that you can use. And all of my tutorials are home F Becerra, which is my username and tutorials. And there you can see the 3 tutorials plus 2 images. If not, I'm gonna upload them to the GitHub anyway, but I'm gonna go over them quickly so that you know what they are about. So the first one is about types of plots, trying to think about like many different ways of representing one data set. In this case, I took as an example the number of deaths per month since 2000 for comunas in Chile. Comunas is like the city equivalent in the US. And the context of this data set is the COVID-19 pandemic. So the whole idea is to think about how we can represent that data in different ways. And I walk you through 2 different ways that I thought about. One is the default line plot, and we start to see like what we can discover from the data, spikes, or this one, for example, or these drops, or this tendency. I analyze all of that on the notebook. And also start making some modifications to make it look better. I don't like this white space. I'm like super confused. What year are these each line? So we need to, and also like the labels here are like just not working. So I go through improving a little bit the plot, but the important part is also about thinking about a different representation. This is related to the concept of design fixation that I talked about during the talk. So thinking beyond that, like trying to find new ways of representing the data. This is exactly the same data, but using heat maps now. I didn't like the color scale, so I just changed it, and suddenly this reveals way more information about the same data set. Now it's easy to see that, yes, there's a spike here due to COVID-19. There's also another spike here in July 2014. I have no idea why. And we start to see this trend that there are more deaths around June, July, August, which makes sense because those are winter months in Chile, etc. So there are 2 ways of plotting exactly the same data. They have different purposes, and for the user it's easier here to compare across the same month, different years, or 1 year, different months, etc. So the intention behind the plot is what's gonna tell you what kind of chart you finally use. The second notebook is about improving the visuals of our plot based on the design principles of maximizing data ink ratio to avoid chart junk, and like how we can improve simple plots here. So the data is the number of women and men enrolled in Chilean political parties. And what I want to do here is to plot the percent of women and the percent of men. So by default, I'm just gonna use a very generic bar chart. So I go from the bar chart that Pandas generate. I start playing with it, making it look nicer, trying to change the way I communicate the data to make it easier for the user to see which one is the one that has less women, the one that has the most percentage of women, etc. So I started like iterating over it, adding more things, taking up some things, etc. So there's a whole discussion, and the final plot is this one. That to me looks much nicer, much cleaner, has more space. It is easier to see the order, etc. And the final notebook is a challenge for you that you can apply things that you learn in the first and the second notebook. So the challenge is to reproduce one of these plots from the Financial Times. They've done a really great job tracking the COVID-19 pandemic. So I saw these plots and I was like, oh, they actually look like a heat map. So since we already talked about heat map, we already talked about simplifying and beautifying your plot, you can totally use those skills to try to reproduce these using Matplotlib. So I give you a little introduction on the data, a little bit of pre-processing, and then it's up to you to make your own plot. I did this with just like a few lines of code. So at this point, you need to start adding labels, the dates here, a title, the continent, etc. So I think it's really fun to play with it, and you can put into practice everything that we've learned so far. So yeah.